Welcome to the pre-recording of Lecture 3 of MCS 260. So this is the first part of the second session in our 8-week summer course. In a way, we are starting still over again, although I hope that by now you have Jupyter Lab and Python installed on your computer. So this is the main action item for this week. What is scheduled for this lecture are aspects of computers called machines, um, and we will see that every object that we manipulate in Python has a type. In specifics, we will talk about number types. What are computers? So let's talk about the von Neumann machine, which is in some sense an abstract concept, but also could be referred to an actual machine. So this is a historical picture. The date is 1952. That's the year in which the first computer at the Institute for Advanced Study was operational. So I got this picture from a website, a historical website on mathematicians. There are several aspects I want to indicate. So first, if you look at the computer, then unless I'm telling you that actually it is a computer, you would not recognize it as a computer. So unlike, for example, if you think about automobiles, you could still, a car from 100 years ago, you would still recognize that it is a car. Here it was not even 100 years ago, so you can see the change in technology. The other aspect I want to point out is the advanced study. So this course, Introduction to Computer Science, is about using a computer. What using a computer meant today and back in those days. So the computer was built in the 40s actually. Was also a result of the war effort. It's not the very first computer. It's the first computer at the Advanced Institute for Advanced Study. But what I would like to indicate that at that time, using a computer meant different things from what we meant now. Nevertheless, the concept of the von Neumann machine is still very relevant today. So the original design of the computer was keeping data and instructions, treating them in as the same. So we would think about, when we think about data, numbers, for example, and instructions collected in programs, we would logically consider them as separately. But the main idea was to store programs and data in the same at the same locations in same memory. So we distinguished 5 parts in a computer. So the first 3, if you want, binary. So we have the internals, processor, memory, storage, and then the peripherals, the externals, and the system bus. What is important, what characterized the von Neumann machine are the fetching of the instructions, decoding of the instructions, and the execution of the instructions. So these are the stages that are regulated by the system clock. So the frequency of the system clock determines the speed at which the computer operates. So the first exercise for this lecture is to figure out the specifications of your computer and interpret this, write this in your own words. So we will talk about numbers. So we have introduced, or we have talked about the binary, the hexadecimal notation of numbers. So in binary, we use bits. 8 bits form a byte, so this is why the octal number system might be appropriate as well as an alternative number system. A byte is one memory cell. Typically, you cannot address, you cannot locate any item bit by bit, but you can locate them as a byte. Byte, so it is used to decode information. So how do you represent the letter A? Um, how do you represent the number 1? It's not 0, 0, 0 and then 1, not 7 zeros and 1. There is a specific convention for this. So there is the ASCII format. That's the American standard. But there is the Unicode, the universal code, that is more extensive and that can be used to represent a whole wide range of symbols in now 16 bits. All right, let's go back to the components. So the processor executes instructions, also controls the execution. So it has a control unit, an arithmetic unit, and the system clock also belongs to the processor. So these are the three main parts of a processor, the central processor. These are the units. Then also part of the central processor unit are the registers. So registers are memory cells that are closest to the processor units. It is the memory cells that can be accessed extremely quickly. So all data typically is moved into registers. So there are several registers. Again, if you think in binary, you have data and instructions. But there are working registers, registers that contain program counters, registers that contain operands of operations. So the status register is also an important register. Uh, the bottom line is that registers are where the processor stores its data. So that is on top of the hierarchy. So there is in some sense a pyramid. So registers are the fastest. And why not use all of them? Well, they are volatile. Once the instruction is executed, the data disappears. So also volatile and less in memory. So there is main memory. In the last session, we just said this is the random access memory, but the main memory is separated into read-only memory. That stores part of the operating system that actually never changes. So this is also typically belonging to the hardware. So in the last session, we made a sharp distinction between hardware and software. The micro programs that never change, stored in read-only memory, are actually a hybrid. There are programs, but they actually should be considered also as part of the hardware. So what is important about memory is its capacity. So again, if you look up the specifications of your computer, an important characteristic is the size of your main memory. We will talk about the number types. There are integer types that are machine integers. We have bytes, and a byte is the group of 8 bits. But typically we talk about 32 bits or 64-bit integer numbers. Everything that you store in main memory has an address. So there is where the program can locate the data. And there are 32-bit and 64-bit addressing mechanisms. Um, Most computers are 64 bits, so this is how you can often see the age of a computer as well. So 32-bit addressing mechanism is sufficient to address 40 gigabytes of RAM. So here the gigabyte, we have two, we think of the powers in two. 2 to the power 10 is 1024. So that is a kilobyte. Kilo is 1000, but 1024 is a kilobyte. 2 to the power 20 is about 1 million, a little bit over. That is a megabyte, so a million bytes. You can still do this with 20 bits. With 30 bits, you get into the range of a trillion bytes. And you have two more bits, so you can actually access 4 million, uh, 4 billion uh, bytes. So we have, I misspoke with trillion. So we have thousand, a million, a billion, and then a trillion. And then beyond that, so we are actually, as far as computing goes, in the exascale already. So we're living in the 64-bit machine world. So I hand-wavingly described the notation gigabyte. Look this up. So this is 4 billion bytes. 2 to the power 20, 4 times 2 to the power 20, 2 to the power 32. There are the registers and the main memory. In between, there is the cache. So if you look up the specifications of your computer, it may list the levels of cache even. So there are several layers in between the registers and the main memory. If you look up a computer, processor speed is important. Memory speed is often just as important because most programs are actually memory bound, not compute bound. All right. Um, Memory and storage. In the last session, we distinguished memory, which was volatile, storage is persistent. Also here we can classify older technology are tapes and floppy disks. In some sense, a CD-ROM and a DVD would also might be classified now as older technology. My the first laptops that I bought, they all had CD-ROMs and DVDs. Now they have disappeared from laptops. You still have memory sticks. So that is actually the reason why CD-ROMs are not so commonly used anymore. So you have still widely used memory keys. They are portable hard drives. Another important characteristic of your computer, look up the hard drive. And typically this is already expressed often in terabytes. So tera is the next level after the gigabyte. So you have already terabyte drives. That tera stands for trillion. So trillion amount of bytes that you can store. Organization of information is important. We organize things in folders. In the age of search engines, that might be not so relevant anymore. I used to store all my personal mail in separate folders, but I gave up on this after a while. But still, it is important if you look into, if you search if you want to know where your computer installs certain softwares, it is important that on a computer you have where your operating stores the installed software. Uh, that is still organized in a very nice and hierarchical fashion. The input and output. Hand wavingly, I referred to this as the keyboard and the screen. And in some sense, if you think about the laptop, the keyboard and the screen, they are actually all one piece. In some sense, we can be very careless about this. But an important component of your computer is the video card or the graphics card. Uh, Graphics cards have become more powerful than the central processing unit. So there is the concept of the graphics processing units, and the performance of those graphics cards is often already expressed in the trillions as well. So this is not really in the scope of this course, but notice that the computer that you buy, uh, if you compare generations of computers, what has improved steadily are the video cards, or to give us much better quality of the uh, output. Think about video games, of course, but also think about computing power. All right, so this is the last slide on the to give the complete picture of the peripherals. There is the system bus, and again, one line, what does the system bus do? It actually coordinates the communication of the components with the peripherals. But also here, data consists of actual data, what we consider as data, but data also where it is locating, the addressing, and then also the instructions that are executed for doing the transfers. So what we mean by data is always a sequence of bits, but what it actually means, it could be actual data that you transfer, the number. It is where it is located, the addressing, and it could also be the instruction that is used to manipulate the data. So this still goes back to von Neumann, the idea that it's all data. So do not this the versatility and the usefulness of a computer is just that everything is sequence of zeros and ones. All right. We are programmers, so we have learned a little bit on how a computer is organized. Now, what does this mean for a programmer? Well, think about what happens if you execute your first program. And this is also something that I hope that this is our second session, but I hope that after installing your environment, Jupyter Lab and the Python interpreter, that you can do the hello world. One instruction, that is the simplicity of Python. But if you think about in the von Neumann world, what actually needs to happen is the fetch, the decode before, and then the execution. So we had the Python virtual machine as the image that we have. Below the Python virtual machine, there is a lot more that is involved. So in some sense, Python is a high level language that allows us to think in the abstract. Uh, as a programmer, it's often good that you can think and reflect, consider what it is that is actually happening when you execute an instruction. So historically, a lot needed to happen for the print hello world. Okay, um, data. Data are actually sequences of bits, and in a way, and this is a mathematical computer science course, everything is a number, if if you like. Logically, we distinguish between exact and floating point numbers. You can already say, well, hey, a second, everything should be exact. But when it gets to very large numbers, what actually matters is the exponent. And this is in some sense what we did when we talked about kilos, millions, uh, billions, and trillions. What you actually refer to when you talk about 4 gigabyte, 4 billion bytes, you actually talk about an exponent, 2 to the power 30. Um, so if you think about the number, then the fact that you have 4 gigabyte or 3 gigabyte or 4 gigabyte, it would be always a multiple of 2, but still it would not matter that much. So what matters is that you have gigabytes of main memory. So the magnitude matters. In Python, integers can become arbitrarily long, which is definitely a blessing. But know that even if you would have terabytes for internal memory, it is still limited. So it's another course, symbolic computation, where we are worried about expressions. Well, so working with floating point numbers is important. And what you would need to know for this course is the notion of machine precision. It's the smallest positive number that when you add it to 1 is still a number different from 1. So if you start up adding all kinds of small numbers, at some point you won't notice the difference anymore. And that can lead to quite unexpected results. So be careful about this. Also, when you format numbers for floating point numbers, it actually may matter that you know the scientific notation. Again, for machine precision, something very small, 2 to the power minus 52. In numerical analysis, we will very precisely get to this minus 52. Here, we can experimentally determine what is this machine precision. Um, So if you format numbers, or if you look at numbers, so by default it would write 1.267, and you would think this is a small number, 1.267, until you get to the e plus 30. And actually e plus 30 means 10 to the power 30. So you should read floating point numbers from the right to the left. The magnitude matters most. Okay, Python provides the fractions module and the decimal module. The fractions module allows for rational arithmetic. The decimal module provides arbitrary precision floating point arithmetic, working with decimal, working with 10 base 10. Um, so there are modules. So you have to do something special to use it, but know that you can use it. So it's not done by default, but there are advantages to using the decimal model and the fractions module. So again, these are hybrids then. With fractions, you can approximate rational numbers. With decimals, you can work more closer to what you as a human uh, experience. 1 over 10 is exact in decimal, it is not in binary. Be careful of this. Okay, I'm halfway into this lecture, and in the previous two lectures I went over time. I'm planning not to do this and to finish in time. Okay, here are the exercises. Up to this point, you should be able to do the first half of the exercises. So I introduced the computer in the historical way. This has the advantage that the slides don't have to be updated each time the course is being taught. But you should actually look at your own computer now and figure out the system administration. This will be very technical and very overwhelming, but write one summary about the essential characteristics. When you bought a computer, what were you looking for? It might have been that the price was the most constraining factor, but what did you get for that price? And you could also, if you are more an economical person, you could, if you have multiple computers, you could expand on this. If you have a higher price range computer, what do you actually get for this? Um, Second exercise, one of the last exercises in the first session was to describe the algorithm to sum up two integers given by sequences of digits. Uh, Now describe at the final level what actually happens when you sum two numbers. Describe the fetch, decode, execute cycle. What needs to happen? For exercise 3, perhaps you know it already. What is Moore's law? Look it up if you do not know it. You can use ChatGPT or any search engine, but what is important here is that you don't copy and paste what Moore's law is. Write it in your own words. So what is important is that you can summarize things in your own words. Exercise 3 is similar to exercise 1. So summarize in your own work what is the relevance, what did you learn, what struck you and struck you when you looked that up. You can again, who was Moore? That's another personal way of looking at computer science. Who are the main figures in computer science? Technology wise, what does it mean still? Does Moore's law, is it still relevant today? Okay, so this concludes the first part of this lecture, and I actually should have budgeted 20 minutes. I went into the half hour. I'm presenting this within a Jupyter lab, which is an integrated environment. So I click on the Launcher tab now. So in the Launcher tab, you see the notebook environment. So now would be a good time to make your own notebook if you haven't done this already. Following through these pre-recordings, what you could do is open a notebook and actually take notes. So you can take notes in the conventional way, paper and pencil, but you can also take notes in an electronic notebook. YouTube videos, you can pause them. So you can, of course, this gets transcribed as well. I'm um, babbling too much. So Jupyter stands for Julia, which is an alternative language, a newer language. So it also incorporates Markdown text. So it can be used to execute programs. So here you see the nice environment that it brings to you. So the action item that was recommended for the first session was to install Jupyter Lab. If you haven't done this, don't panic. There's still time. If you need help with this, please contact me. Please ask the teaching assistant. But it is kind of critical that in this computer literacy course that you can install software on your own computer. We are living also in the age of the cloud computing. You can run through this course. If you don't do this, you can still pass the course. Don't worry. We live in the age of cloud computing as well, but it is important that you can install software as well. All right. I have prepared this lecture. Um, And in some sense, the purpose of this pre-recordings is that it is more structured and organized. So I will go in 10 minutes, I will scroll through this Jupyter notebook. What is important is that now we are using the notebook as a calculator. In the next session, in the next lecture, second part of this session, I will explain how to use the Jupyter Notebook as a development tool to develop Python programs. Here we use it as a calculator. In some sense, we use it to explore Python. And we document our work. So there are two important markdown cells. So there is the plain text. So you can actually run plain text. So there are the selections. So there are, by default it's a code cell, and then there are the runs. So if you can click on the icon each time, but you see there is a shortcut, Shift Enter. I actually click on the icon because I still have the reflex to type enter, which is a new line. Here is an important item, that is the header. So defining a header, so I convert it to raw to see the input, what you would type. So you would change the cell into Markdown and then start typing. That first symbol here indicates that it is a header. If you then run, so go to the icon, then it will format it. I emphasize this because when you submit homework, please use this to indicate that you are solving exercise number of lecture number. That makes it for us grading a lot easier. Uh, that's the first formatting. The other formatting is what I like to use, the backticks. So backticks are used to indicate that it's not really um, the characters, but it means something different. So the exponentiation in Python is double star, star, star. It's it's kind of intuitive. The multiplication is a star, so the exponentiation is to the power. It's a more powerful multiplication. It's not the hat. As an exercise, I want you to figure out what is the hat. Python has the built-in help. So there is always the reflex to open a search engine or to ask external resources. And that is something that often you have to do. But it's also good that you know the resources, the fastest resources that you have often available is the help in Python. Okay, how do you make long integers? Very easy. So 2 to the power 10 is 1 kilo, is 1024. Doing to the power 10 again is doing that 10 times over again. And that gives you a very long integer. 30 decimal places long. It is 10 to the power 30 in the floating point. Notation. Notice that it is subtle. If you do 2 to the power 2, just as the integer 2, then you get an exact number. If you do 2.0, so 2.0 is a float. The number 2 is an int. So you can query this with the type. So the instructions 3 and 4 here give you the type. I will explain this much more carefully in the next lecture. So Python has dynamic typing. Everything has a type, what you compute. And it is important. So Python often tries to figure out automatically what type you use. But you could say that for me, this is too subtle. I mean, I might have just typed 2 points and then I would have gotten a float number. But actually, I wanted something different. So um, note that the typing, the dynamic typing, may often lead to very strange results. Here you see the introduction of machine precision. So if you add 2 to the power minus 53 to 1, then you don't see a difference with 1 anymore. So this is an illustration of the machine precision. So the machine precision is expressed in the powers of 2. Float is a machine integer. If you work with integer numbers, you work with software-driven, software-defined integer arithmetic. It has repercussions for the um, type of operations that you can do. Here you see the fractions. So when you do the division, and that's actually another exercise, perhaps actually I can, if I have more time, and I will have time, see how you can explain this. So Python is in some sense inconsistent, so it does exact integer arithmetic, but it doesn't convert to rational arithmetic automatically. So let me do this. So let me, as an interludium, so insert a cell. So I will add a cell and I will move the cell up. So let me add a subsection here. So that could be another good way. So a subtitle. So this is a smaller subtitle. So the integer division. So let me document what I was about to say. Python does by default exact integer arithmetic, but not rational arithmetic. So this is where the difference goes with computer algebra. So I mentioned SymPy and SageMath. Um, they are more consistent in their number types. So if you do 1 divided by 3, then see what happens. You get 0.33333. Oops. Uh, so note also, by the way, this is now my first instruction. If you download a Jupyter notebook, actually what I did this morning, I was just clicking on the Jupyter notebook and it showed me what was saved. So this is another issue that I should explain, but let me just make the point here. Um, there is the integer division, and that is the double slash. So this is even worse if you like. So there is Python 2, Python 3. So this actually changed from Python 2 to Python 3. So Python 3 was supposed to be an improvement, but it got it wrong, in my opinion, in both ends. So both answers are, uh, well, they are right. So let me now not be too. So mathematically, both answers are wrong. So this is where, as a mathematician and as a computer algebraist, I should perhaps say, hey, I don't agree with this. But from a computer perspective, from a computer science perspective, they are perfectly valid if we understand the logic of the typing. So the operator on integers returns a machine float. The operator slash /s returns the result, the quotient of the integer division. So that's it. Um, So in a future version, perhaps Python 4, the fractions type of the rational arithmetic could be automatically built in. But the point is that conforming many other conventional programming languages that work with machine integers, then the slash is still the integer division. Uh, Python deviates a little bit from that. So you see, the 1 over 3 is actually also wrong if you think about floating point arithmetic. So while it's wrong and not wrong, 1 over 3 is not 0.333 because it would be dot, 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 dot. So there is an important error here. In binary, we cannot, I'm sorry, in decimal, we cannot represent 1 over 3 correctly. It would be trivial in a base 3 number system. Okay, there it would be 0.1. 0.1 is correct in a decimal system, but it's not in a binary system. So the base of the system matters. So you get different representation errors of the numbers. All right, I already answered with this one of the exercises. But try to rephrase this in your own words a little bit. Make sure that you understand this in the way you can say it. Okay, a rational arithmetic, if you want to do it, well, you do it automatically in a computer algebra system. You can do it in Python as well with the fractions module. So you have to import the fraction from fractions, import fractions. So Python is case sensitive. If you write f with a big letter as fraction, it's different from little one. So notice this. So I had 1 over 3. So if you have 1/3, then it will show you as 1 comma 3. So in some sense we are running ahead a little bit, but you could see the fraction type, the 1/3, as a function that stores data. So the fraction is the name of the type. The 1 comma 3 stores the numerator and the denominator. So you can query this explicitly. And you can compute with this. So here you see when you add 1 over 3 and 2 over 5, you get 11 over 15. Related to this is the greatest common divisor. So we explained, or actually in the lecture I ran out of time, but in the pre-recording I went through Euclid's algorithm as one of the ancient algorithms, going back to Euclid. Now, we went carefully, in the pre-recording at least, through the definition of the greatest common divisor and Euclid's algorithm as well. Well, from a mainly utilitarian perspective, if you ever have to compute a greatest common divisor quickly, well, import the GCD from the math module. The math module that also stores a definition of pi, the floating point representation of pi. So the GCD is related to the fractions. And actually it used to be that the GCD was in the fractions module. Okay, ASCII codes and strings. So everything inside a computer is a sequence of strings, is a sequence of bits. So also the letters and the numbers. I said check out the ASCII code for 1. So there is the difference between the character 1 and the number 1. So I try to indicate this with the backticks when I write about it. The 1 is the number 1, which is universal in any number system, in any notation. It's not a bit, it is 1. But there is the character 1. The character 1 is different from the number 1. So the character 1 is what we use to represent the number 1. Here you see the ASCII code, the way the convention is in the American standard to represent the characters. You can go from the ASCII code into the numerical, and you can also go backwards. Notice that you can tell from the way the output is formatted what the type is. So you can infer that the result of ORD is a number, and the result of CHR, short for character, is actually a string. So, and now this, to my shame, I discover a type error. So let me show how you fix type errors. So I go to raw and I fix this type error real quick and typeset it. Okay, so this is the last thing that I want to explain. So now, wait a minute, what is Unicode? So why do you explain ASCII code and not Unicode to us? Well, please look it up. So we may get to this in a later session. So the operators, so the plus on strings concatenates. The percent operator is used in two ways. It is used as a formatting operator, and it's also used in a formatting string. So if you want to format a number with a certain precision in scientific notation, you use the percent operator, where the second operator is the name of the variable that refers to the number, that holds the number, and where the first argument is a string. So this is an operation that has two operands. Okay, and I'm violate now my promise not to go over time. So I have given a first introduction of using Python as a calculator in a Jupyter notebook. And I hope that by now it should be uh, clear to solve these exercises 4, 5, and 6. I started the answer to part 5. Write it in your own words and do the help on divmod. We will implement in Python the greatest common divisor, Euclid's algorithm, but it's already there in the math module. But divmod is a very good, useful operation to this. We can concatenate strings. Find the ASCII code representation for hello, as representing this as one bit string. And I hope this was not a too confusing lecture, illustrating the some terminology and also the introducing the number typing mechanism in Python.